Hello, everyone. Welcome to the next part, second part of this two-part video lecture of week 13 of the deep learning course. In the previous lecture, we learned about uh, autoencoder, which is a self-supervised learning algorithm. So and also you learned about how to compress the input data into a smaller dimensional bottleneck layer, we call it a code layer. And I mean, first part is the encoding part that digests that uh, input data into the smaller dimension. And the decoder layer uses that smaller dimension to get or reconstruct the original data. So here in this video, we'll talk about segmentation, how to extend that idea to do segmentation. And we need to learn actually what segmentation is and then try to build on top of that. All right, so let's begin. So here are a couple of study materials that you must read. This is a tutorial. All of these are tutorial on semantic segmentation. So, and also UNet, the original author of the UNet architectures that we'll learn today, Olaf et al. Just take a look at these articles. All right, so pretty basic things first. The strength of computer vision. So computer vision is an interdisciplinary field to enable computing devices to make a level of understanding from visual images, right? Digital images or videos. And videos are essentially stack of images. And deep learning has enabled the field of computer vision to progress rapidly over the years. So first task in computer vision is image classifications that we have done already, how to do that. The problem is given a set of discrete classes, say for example, cat, dog, truck, etc. And you're given an image, you just say this is a dog image or not, right? So given the entire image, you're classifying whether the image is a dog or a cat and so on and so forth. So it is very high dimensional, subjective in a way that given the entire image is about dog, which isn't true all the ways. Maybe if an image contains a dog and a cat, did you try? I mean, you think about that, the model that you have built over the past couple of months, what is going to do? So it will definitely misclassify. It is definitely going to misclassify the data set or data samples. Sorry about that. All right, so proceeding to the next task, which is called classification with localization, so which is building on top of the task one, which is entire image classification. Here you classify, you add bounding box to the class levels. So given an image, you just enclose where the class, the say horse class exists. So there's actually an image containing multiple categories or multiple objects of different categories can be enclosed and classified without confusion, right? So, so definitely this is the task. This is task 2, and the task 3 is object detection, right? So object detection extends the localization to the next level, right? So we expect to detect multiple objects in the same image, right? So so here you see that actually there might be overlapping between objects. This part is localized. I mean, you put bounding box around the dog, And also object localization, object detection. We tend to use say a square or rectangle to define that bounding box. So this is a dog, and these bounding box represents an object of bicycle. This is car, and so on and so forth. So we expect to detect multiple objects, and there might be multiple dogs. So, but you have to localize, and identify and put these coordinates of this uh, bounding box. And the coordinates is it is used, I mean, as a, how to say it, a rectangle. It's easy to define. The coordinates is a top left corner, uh, coordinate x and y axis of the top left corner, and then width and height. That should be sufficient. You could have store the bottom right corner, the xy coordinate as well. The fourth task is called the semantic segmentation, which is the topic for today. Semantic segmentation is on top of object detection. We'd like to segment the entire image into different classes. So previously, the rectangles were used to put define as a bounding box. So here we would like to put some details on that. So we'd like to segment entirely actually what part of the image belongs to a particular, say, a person. So, and what part of the image is belongs to bicycle class, and what part belongs to the background. So this is actually segmentation. I mean, we use fully convolutional neural network to do semantic segmentation. All right, so I mean, you can also think about semantic segmentation as pixel-wise classifier, right? So uh, every pixel in the image. So I mean, think about it as building a classifier which is predicting class level, one of the three class level for each pixel, whether it's this pixel belongs to a person or a bicycle or a background. We can pretty much define a pixel by pixel classification to define or to, how to say, get or solve the problem of semantic segmentation. But in turn, that would make the model really complex. Say, for example, that in the data dimension, input data dimension is, if it is 100 by 100, so it is going to be a 10,000 dimensional. I mean, your output layer is going to contain 10,000 dimensions, right? So it's I mean, uh, it's difficult to, how to say, backpropagate, and your model complexity is going to rise. And also task 5 is called instance segmentation. Is so besides semantic segmentation, you'd like to identify actually which, definitely it's an extension to the semantic segmentation. You'd like to know exactly who is who. Person one, person two, multiple objects is segmented properly with instance segmentation. Now that we have learned about the backgrounds of semantic segmentation, uh, let's see a demo here. So given an image, so you see there's the different versions of let's we can stop it. So if you see the caption here, so the input image and different segmentation algorithms were used to segment the entire image. So that's one of the demo that actually that different color tells that actually this belongs to one category, this belongs to another category, and so on and so forth. So this is the input image. This is the ground truth segmentation, and different color tells. So the purple color for a pixel tells that this pixel belongs to a car. Blue probably indicate that this pixel belongs to a sidewalk. This yellow or very light yellow color may tell you that this light post, landscape, and so on. So different color tells the category of different classes. And once you put that, uh, the entire image gets segmented. This is a solution. I mean, the model was trained to using fully convolution neural network called FCN 8-layer fully convolution neural network. This is the answer. This is the solution. I mean, this is the prediction of the segmentation. This is the segmentation result. I mean, to say in another way. So this is a segmentation result, which is pretty good, right? This is fully convolution neural network, which is a way simpler AlexNet model. So this is, I mean, a little worse than FCN 8, right? So it simplifies this. So, so the key to understanding the segmentation, semantic segmentation procedure is to be able to understand what convolution operation is. You're no strangers to this. So convolution operation is essentially performing a weighted sum with weighted sum calculation on the input, and it preserves the weight. I mean, preserves the cement. What's it? The shape of the input image, the structural similarity or structural pattern of a given image, as we see here. And the purpose of convolution layers are to extract features from the input. And we use different kernels, and to produce different feature maps. And also, we have learned this when we discussed about convolutional neural network is given a certain input dimension, certain number of filters, and a certain size of the filters, what should be the output dimension? We played with this type of formula to detect that. But using that, you see actually that the convolution convolution layers output, which is what we call feature map, extracts patterns from the original data, and we subsequently add more convolution layers to again get hierarchy of those patterns. There's another operation called max pooling operation, which also reduces the size besides convolution layer. So convolution layer reduces the size. Max pooling also reduces the size of these feature maps. And you see here, so downsampling, so convolution and max pooling are the two operations in two layers in convolution neural network that reduces the size of the input shape, right? So meaning to say that the dimension of the input gets reduced if we use convolution and max pooling, right? And so now let's recall back to autoencoder. The encoding, the purpose is to create a bottleneck. So we will be using convolution and max pooling of the given input image to get down or create or achieve that bottleneck. Also, these two operations might be of interest. So the downsampling, by downsampling, the model better understands what is present in the image, what we call the patterns, right? So we know that not every pixel in a given image is useful to characterize that to be a dog, right, or a cat, and so on and so forth. We would like to know actually what, if it is an edge or say, structure of edges, for the round shape in the pattern, one sort of patterns based on the previously extracted patterns. We know that actually that the downsampling, so max pooling of convolution layers, uh, uh, gives you that type of what information. But in doing so, actually, it loses the information, what do we call where, right? Because it reduces the size and shape of the input image. So you're losing actually exactly where that pattern occurs as you move on to the next convolution layers or max pooling layer. But if you do segmentation, you know that actually we need both, right? We need to learn the pattern so that we can characterize each pixel to belong to a person or a cat or a dog and so on and so forth. So we'd like to the what information, the pattern, and at the same time we need to know actually pixel level information that exactly where that happened. Right? So this is a challenge to that. So that's one of the key observation that we need to do that. So in order to achieve that, I mean, blend of these two, I mean, so addition of these two information, so what information and where information, uh, uh, segmentation algorithms tend to use the inverse of the convolution operation, because convolution operation reduces the size of the input data. So there is an operation, what we call deconvolution, gets you back to the original uh, input. So just an example, say if this is the input image and this is the kernel, and you know that you apply this kernel onto this part first, and you get 122. And then you slide the kernel over to the next available frame, which is here, and you get 148, and then you move or slide the kernel down here, and you get 126, and again you slide it over to the right, and you get 134. So this is the compressed feature map. So this is a 4 by 4 dimensional input gets reduced to this, right? So now we need to deconvolve it, right? So from the say if this is a one feature map, we'd like to extract that input image, right? So how to do that? This is actually, and also this is a one-to-many mapping, and since we are applying gradient descent backpropagation, so we can reduce that one-to-many to some or narrow down the search space so that it greatly resembles to the original size and shape of the input. All right, so, and I've discussed this when I talked about convolution operation, that actually convolution operation in a deep convolutional neural network were conceived or maybe implemented as a matrix multiplication. So where kernel is a matrix, input image is a matrix, and kernel operation, the convolution operation, was rearranged in a way so that at the end, the kernel is placed in a way, what we call the kernel matrix, so that if you multiply it with the flattened input image, you get that exact value for the, the feature map. Right? So I've talked about this before, so I just want to just revisit that. And you see that this is you receive the 4-dimensional feature map if you do that strategically. And your compute framework like TensorFlow, PyTorch can do matrix multiplication very well. So this is the, I mean, so this is the kernel matrix that we prepared based on, and this is the input image. You get a 4-dimensional feature map So now the deconvolution is, so you have this, so you take the transpose of the kernel matrix and you multiply with the feature map and you get the input image, right? So this is called the transposed convolution operation. And in turn, actually, you get the original shape, size and shape of the input data. So that's it. So this is what we call inverse of upsampling, inverse of downsampling. We call it upsampling, and that's pretty much the heart of the UNet architecture. You'll hear about UNet in other. I mean, definitely in deep learning, whenever people are talking about segmentation, UNet is by far the most popular architecture to do segmentation, and it utilizes at first actually you might. So this is the conceptual or architecture for UNet. You might get I mean, upset, overwhelmed with the numbers and the structure, but it has a first the property is it has the U shape, and this U shape is there for a good reason, because it first extracts the what information by creating a bottleneck here. So initially, maybe the input data could be 572 by 572, just a hypothetical example. Is from the original paper of UNet, and you get to the 124 I mean 1024 dimensional bottleneck. You create that bottleneck, so you've got your what information. I mean the patterns needed to classify each and every pixel to belong to a particular class. So this pixel is background, this pixel is person, this pixel is a blood vessel, and so on and so forth. And once you do, then you have to reconstruct. It's what we will be using the transpose convolution, which is the upsampling strategy, to get to the segmentation result, right? So this is the legend that was used in this architecture, and here you see that these are, I mean, there's a bunch of convolution operations. This is a convolution with 3x3 kernel with rectified linear unit as activation, and you move on and you move on. So there's 3 convolution layers. Then so this is a downsampling. I mean, max pooling operation was used. I mean, convolution is also a downsampling operation. So you downsample and then you you apply max pooling, and then again uh, apply a bunch of convolution, and then uh, you max pool and so on and so forth until you reach to here 1024 dimensional bottleneck. You create that bottleneck. So this is the encoder branch. So UNet essentially is an autoencoder. But by looking at the numbers of the kernel, you see that initially we had 64 kernels and then once we downsample, meaning that once we apply max pooling, we double the number of kernels in each one of the subsequent convolution layers. So meaning actually that we would like to apply as more kernels to learn a small piece of data, right? So that actually we don't lose the what information, meaning that we don't lose any patterns. So we increase the number of features or the filters in every time that we reduce the size and shape of the input image. Once we are here, we turn back. So this you see that actually, since this is an U shape, so the decoder branch is going to do the upsampling, and in doing so, actually, what does it do is that it copies the uh, the 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 component or the output from of the encoder, and it uses that because you need to. This is actually the cheating part of the decoder is it because so for semantic segmentation we need the what information and also we need the where information. But the where information from these layers, there is no, I mean, this is a flattened layer. We definitely lost all the location information. So we need to, and this data was obtained from 512 by 512 dimensional data, right? So I'm sorry, 64 by 64 dimensional data. So we have to give it some data. So this is a concatenation of these two data. So 1024 dimensional data was upsampled and we got 64 square data. And then and we upsampled again and we upsampled again. And every single time you see these arrows are kind of, I mean, are cheating in a way to give the decoder some reference point that actually this is where this pattern was originated. So the location information are tagged here, right? So by these concatenation. And at the end, you get the output segmentation map. Wait a second, let's see. So this is I mean, very detailed. So this is a conceptual diagram. This is a detailed diagram of what has happened, and also for the implementation, it gets easier if you use that. Right? And also this is of a different input image, 128 by 128 color image. All right, so let's apply the unit in solving a problem of segmentation, which is called a salt bed identification. So, so this is a challenge from Kaggle. It has some seismographic, it uses seismic imaging to find actually whether there is salt bodies on Earth. And the data, yeah, you can pull that data from Kaggle, and the data dimension is 128 by 128. And you walk through, you get the data X and Y. So the Y is, I mean, so the data set also contains where exactly the data contains. I mean, it also gives you a mask or the true segmentation result so that you can use that as a reference. So just to visualize a couple of things. So we don't, so given any input image, we know this is actually, there is no salt bed available there. And so this is a convolution block. This is the unit based on the architecture that I've shown you. And also this is definitely a deep convolution layer. I mean, definitely the convolution layers are being added here. And we compiled and this is the optimizer was used for binary cross entropy and Adam optimizer. And once you start the training, so this is the architecture. And also I used a couple of callbacks for TensorFlow to run it properly. And finally, usually we save the base model as a H5 object. And I run it for 50 pulp and with batch size 30 and X and Y. And then once I am done, and this is actually input loss plot for validation and also the training loss. As you see here, the base model, when the TensorFlow computational framework stopped, running is at 23-ish April. And once you have the model, you just load the model and you evaluate on the test data that you have. And once you do, actually, you can see actually that this is the seismic input image. This is the ground truth segmentation of the input image, so that you can see actually this is the salt bed, and this is your prediction, right, for each and every pixel. And if you and also salt prediction with sigmoid and salt prediction with binary 0 and 1, which is pretty significantly, I mean, and pretty accurate, right? You plot again. This is another sample data, test data sample. This is the ground truth that there is no salt bed present. Your prediction is correct. And take a look at the predictions and the original, the ground truth segmentation result. And the model predicted quite nicely. And the predictions on the test set. So this is actually a misclassification somehow. It couldn't figure out that. And yeah, so I mean, so this is we extended the idea of autoencoder and also the convolutional neural network. We blend these two to do semantic segmentation. So this becomes a supervised learning algorithm, but under the umbrella of, unsupervised autoencoder. Self-supervised autoencoder, where we provide the the target as the segmentation result. As you see here, that we have to provide these segmentation. So we call it mask. So in segmentation jargon, we call it masks of the input. So that actually it can find actually that at this location the segmentation exists. So this is about the segmentation, and you can pretty much use UNet and also extend the idea of UNet. You can tweak the UNet architecture in the way that you want. There are a bunch of challenges that you can find at Kaggle for semantic segmentation. And also just practice, actually, you can make good use of semantic segmentation in your real world applications that you will be involved with. All right, so that's all for this week on the two things on unsupervised learning. We talked about autoencoder, which is a self-supervised one, and an extension, kind of an extension to that is the semantic segmentation. In the next week, we'll talk about generative model, which is pretty, which has a lot of applications on data generation and change on transformation or image processing. Also, I'll see you next week. Thank you.